Okay, hello everybody. Hopefully this thing is live this time and I don't repeat my past mistakes. Hello. Hello. Um I enjoy doing live streaming, but it's really weird because unless I have a guest on, it feels like I'm talking into the ether because there's nobody here to give me any reactions or anything. I mean, I guess I can look at the cat, but she's always sleeping, so it's like I don't know. She's not super encouraging, I guess. Okay, let's do this. It's been a while since I've done a live stream, so I mean, let's dig in. Let's get started. I changed my background as you can see. This is the normal view from my office here in Seattle. Um, yes. Yes, it is very true. Okay. Let's see. I am going to start the slides now. Let us do that. Okay. My OBS setup. Okay, great. So welcome everybody to the Cool Stuff live stream. My name is Aaron Patterson. I guess you already know that. That's why you're here. Hello. Hi, I'm Aaron. Happy Friday. Happy Friday, everybody. I'm really glad it's Friday. I love Fridays because tomorrow is the weekend and I'm excited for this weekend. This weekend hopefully I'll be able to put together a PCB I've been working on. But I'm waiting for some pieces from China, I guess. They might be in customs. They might get here today. I'm really hoping they do. Anyway, I'm hoping to build a PCB this weekend. If you are doing anything fun this weekend, let me know. I would like to know what folks are doing for fun. Other news, since the last time I did streaming, I switched the switches in my keyboard. I am now using Kayla Box Navies, and these are extremely loud switches, which I love. I love loud switches. So hopefully we will all like. If you don't enjoy the JIT hacking, like maybe you'll enjoy the keyboard ASMR. So today I thought we'd like do a little bit like start with a few basics this time. I don't think I've really talked about what a JIT is necessarily, and I thought maybe it would be like interesting to go from kind of basics and then talk about what is a JIT and then actually get into hacking on TenderJIT today. But a JIT, like for those of you that aren't familiar, a JIT is just a special kind of compiler, and it's a compiler like any other compiler. It's just that this compiler converts our code into machine code, but it waits until runtime. It waits until runtime to do that. Like normally you'd use like Clang or GCC or some like rustc, for example. Those are all examples of ahead of time compilers where like you have some source code and you're like, hey, I want to compile this, and you compile it, and then you run the binary that's spit out. A JIT just waits until runtime to compile the stuff. So it's going through similar steps that any normal compiler would do, but this one's just happening at runtime. Oh, also, if any of you watching have any questions, just put it into the chat. I'm happy to answer any questions as we are going on here. I am popping out the chat now so I can see it easier. So yeah, just like ask a question. I am happy to answer. All right, so a JIT compiler waits until runtime to actually do its job, and all that our JIT compilers are doing is taking the Ruby code that we have written and convert test chat. Please ignore. They're taking the Ruby code that we've written and converting that Ruby code into machine code. So what's really cool about this is instead of like converting all of your Ruby code into Rust code so that you can get machine code, you can just write Ruby code and the JIT compiler will convert your Ruby code into machine code for you. So you just write Ruby, the JIT compiler will go ahead and take your Ruby code and convert that into machine code. So I guess that kind of begs the question: what is machine code? And machine code it's actually very, very simple. It's just a list of bytes. It's literally a string of bytes, and the CPU interprets those bytes. So if you have a list, if you can put together this like list of bytes and you say, hey CPU, I need you to execute this thing, it will do it. And then that's all there is to it. That's machine code. It's just a list of bytes. So you have to put together that list of bytes in a way, like you have to know how the CPU will interpret it, but that's all it is a list of bytes. And you could think of a Rails application as a type of JIT compiler, but instead of compiling to machine code, we're compiling HTML code. So your Rails app, instead of making machine code, it's making HTML code. And I like to think of it that way, as as a way to make a JIT compiler more familiar to web developers. So instead of a CPU interpret, like in the case of a Rails application, instead of a CPU interpreting the bytes, we have a web browser interpreting the bytes, or which those bytes happen to be HTML. So it's like you can think of it in both ways. A Rails application is doing something very similar to what a JIT compiler is doing. So what are the advantages of a JIT compiler? Advantages of a JIT compiler are that we're able to know more information at runtime and customize the machine code that we emit when we get that information. So one thing that's cool about a JIT compiler is, since it's doing its work at runtime, it's able to look at runtime values and then customize the machine code that it outputs to meet those runtime, to better handle those runtime values. So we're able to get more information at runtime than an ahead of time compiler might be able to get. So like I said, we get runtime information. The JIT compiler can wait around and be like, hey, I'm going to let you execute, and then it can start kind of like peek at the runtime values. So an example of this might be like, let's say we have this add code here. Theoretically, like we could take this Ruby code and compile it ahead of time. Like we can look at this and say like, hey, I'm going to compile this. I'm going to run an ahead of time compiler on this and convert it into a binary. The problem is, like, when we turn it into a binary, we have to be able to deal with any type that goes into the add method. So we all know, as Ruby programmers, we know that the plus method could work on numbers, it could work on like integers or floats, also strings. Maybe it could be just like random objects that happen to implement the plus method. And if we were going to do this ahead of time, we would have to take into account every one of those possibilities. So we could produce a binary that would handle all those possibilities, but then we would end up with a very complicated amount of machine code just for this simple method. Now, a JIT compiler can wait around until runtime and take a look at the values of A and B and say, oh, wow, A and B, they're always integers, so I'm only going to emit machine code that's specific for integers. So it's able to know this. It's able to know this at runtime and put together very simple and efficient machine code that an ahead-of-time compiler may not be able to do. Another cool thing is that a JIT compiler can cache values in the machine code to help speed up execution. So, for example, like let's say we have this. We go back to this code example again here. When the JIT compiler sees the values 1 and 2 as parameters, maybe it can cache those immediate values straight into the machine code itself. So like the JIT compiler can say, oh, I see you have this integer literal. I'm just going to put that into the machine code itself. I don't need to go look up what the values were that you put into the text of your code. And the reason I wanted to bring this up is, like, I was talking about how a JIT compiler is similar to a Rails application, where the Rails application is producing HTML. In this case, we can think of like partial caching in a Rails application, where we say like, hey, I'm gonna cache a little bit of this, like this chunk of HTML code. I'm gonna cache that, and then reuse it. And a JIT compiler can do exactly the same thing, but it's just doing it with machine code. So you can think of this in terms of like partial caching in a Rails application. So, oh boy, good job, Aaron. Wrong button. All right. So disadvantages of a JIT, though, like we talked about advantages of JIT, let's talk about disadvantages of the JIT. Unfortunately, this compilation, or the speed gain, is not free. As I like to say, it's really great, but at what cost? Unfortunately, this performance doesn't come for free, and one of the costs that we have to pay is typically memory usage. I didn't know like I didn't know what emoji to use here. I'm imagining this emoji. This person has too many memories, so their head is exploding. So, uh, this performance doesn't come for free, and we pay in terms of memory, and some of the memory cost is like bookkeeping. So not only the machine code that we generated, but also like bookkeeping for the JIT compiler, like the any type of overhead for the JIT compiler itself that the JIT compiler may incur itself, but also like keeping track of runtime information that might cost us memory. The other thing is like warm up. We don't get to top speeds instantly. It takes some time to reach those top speeds. Uh, and but however, like one of the cool things about a JIT compiler is that when we do reach those top speeds, since we're able to take that runtime information into account, the top speed of the machine code produced from a JIT compiler can actually be faster than an ahead of time compiler. So it is absolutely possible for us to write something in Ruby and then have it be JIT compiled and have the speed of that code exceed that of say something written in C or Rust or whatever. So, and it's all due to the fact that we have that runtime information. Now these things like, why do I keep hitting the wrong button? We're doing it live, right? Live stream. uh, these disadvantages are typically like the points where JIT compilers like to compete. So like who can get the top speed, who can reach top speed the fastest, like who has the lowest warm up time, who uses the least amount of memory. So those types of points are where different JIT compilers can compete. And now that we're talking about JIT compiler competition, let us talk about TenderJIT versus YJIT. I want to talk about the differences between these two JITs, and then we'll dive into actually hacking on TenderJIT. Of course, YJIT is written in Rust. If you want to hack on Ruby, and so if you know Ruby and Rust and C and machine code, just those four things, you can work on this JIT. It's written in Rust. TenderJIT is written in pure Ruby, but that's not the whole picture. So let's talk about the ways, like the algorithms that they actually use. YJIT is based off of a technique called lazy basic block versioning, and I put a link there at the bottom, but also there's a QR code that you can like go to. This technique was pioneered or as part of my coworker Maxime's PhD thesis, and you can go read about it there. It's great. It's very cool. So I'm going to explain what lazy basic block versioning is. Lazy basic block version, like what is this technique? Let's try to take a look at it in a practical, like from a practical standpoint. First, in order to explain lazy basic block versioning, we have to define like what is a basic block. And a basic block is just a way to divide up code. So we take code and we divide it into these like basic blocks. And these basic blocks are just chunks of code, and the chunk of code only has one entry point, so you can only enter it in one place, and it could have up to two exit points. So we're gonna split this Ruby code up into basic blocks. So basic blocks for this code might look something like this, where we have an entry, and the entry is just our call to puts. So we say like puts hi, and you'll see at the very bottom of that basic block we have a jump, and it's a conditional jump, and that jump maps to our if statement in the Ruby code. So we say like, hey, if the conditional holds, I need you to jump to the block that's labeled true. So we have that block down there in the middle on the right labeled true. So if it's true, we'll jump to that block. If it's false, we'll jump to the other block. Or it won't jump, it'll just like fall through. But we could have two jumps there. You could think of it as having two jumps. So then the bottom of those two, like either if we go to the false path or the true path, both of those will, just for simplicity's sake, we've written an unconditional jump at the bottom of those to jump to the final block. So this is how we split our code up into what is called basic blocks. Each of these are basic blocks. They only have one entry, and then they have up to two exits. So they have one or two exits. And these basic blocks, when they're arranged into a graph like this, we call that a control flow graph. So this is kind of a control flow graph for this method foo here. So the way lazy basic block versioning works is when the JIT goes to compile this method, it goes ahead, like the JIT says, okay, it's time to pause. I'm going to compile the foo. Like we've hit our call threshold. We're going to compile the foo method. We come in here and we say, oh, okay, it's time to compile this thing. The compiler goes ahead and it compiles its very first block because we know we're going to execute that. But it doesn't know, at the time, it doesn't know if we're going to jump to the true block or the false block. So the way lazy basic block versioning works is it says, okay, well, I'm not gonna compile anything else. I'm just gonna compile this one block, and I'm gonna insert what we call a stub here at the bottom of that block. And you'll see that those labels, I labeled them like compile true and compile false. You'll notice that those labels aren't the same as the two blocks below. What'll happen is when we go ahead and execute this machine code, if we jump to the true case, we're going to jump back into the compiler. So let's imagine X is true, and we say it comes down here and it says like I'm going to jump to the compile true block. That jumps back into the JIT compiler and says like, hey, I need you to compile the true case. Somebody is asking, is the JIT compiler looking at YARV or just, John is asking, is the JIT compiler looking at YARV or just Ruby code string or something else? That's a great question. The JIT compiler is actually looking at the YARV bytecode itself, which we're going to do when we hop into TenderJIT as well. So it just looks at the bytecode and translates that bytecode into machine code. So back to this. The YJIT will say, hey, you jumped to the compile true case. I'm going to go ahead and compile the true block. So we re-enter the compiler. The compiler says, oh, I gotta put my mouse here. Compiler says, okay, let's compile. So the machine code takes a true path. It jumps back into the JIT compiler and says, hey, I need you to compile the true path. It compiles the true path. So we actually compile this block right here. And again, it doesn't know where it's going to jump from there. So it inserts a stub. So we say like, it's clear to us that, yeah, it's going to jump to finish. But the algorithm is like, we don't know where we're going to jump. So we're just going to insert a stub here. So after we've compiled the true block, it goes ahead and it actually rewrites the previous block and says, okay, we know, like we have now generated that new true block and we know that we're going to jump there if the case is true. So it goes ahead and rewrites that previous block to say, hey, if the case is true, I need you to jump to this block. So it's literally rewriting the machine code that was previously written out. So then again, like we just followed the algorithm exactly the same way. It says like, hey, we jump to compile finish. That goes back into the JIT compiler. JIT compiler says, hey, we're going to compile the finish block. Goes ahead, compiles the finish block, and then it rewrites the previous block to say we're going to jump into that finishing block. So this way, like, this is why it's called lazy, is because we don't actually compile any of these blocks until we get to them. Like, it doesn't compile anything unless that thing is actually being used. So you'll notice when we walked through this particular algorithm, like we never actually compiled the false case, like the false block. That's because we never used the false block. So that's a really cool feature of this algorithm. So we end up only compiling what we need. So we only compile the branches of code that we actually use in our program. The other cool thing about this is that it's able to help us decrease runtime checks. So let's say, for example, we have some code that's calling a bunch of methods on self, and the first time, like in a normal compiler, we would have to check the receiver type all the time on every one of those method calls, where YJIT is able to say like, okay, well, I did the check once, and I know any subsequent blocks based off of this, that check has already been performed. So I don't need to do that check multiple times. I just do it once here, and then all the branches that go off of it basically reuse that previous check. So lazy basic block versioning helps us reduce those assertions in the generated machine code. So RJIT is also using lazy basic block versioning. It's basically just RJIT is just a port of YJIT to Ruby. So it's basically the same algorithm just in Ruby. TenderJIT, the very first version of TenderJIT was also using lazy basic block versioning. And to be honest, like the reason I wrote TenderJIT, the first version, is because like I didn't really understand how lazy basic block versioning worked really well. And I'm a very much like, I don't know. I learned by doing things, so I wanted to try implementing it, running into problems, and then seeing how to solve those problems. So I decided to write it in Ruby, and that's TenderJIT 1.0. TenderJIT 2.0, however, I have completely rewritten it. It is totally different now, and it is now using a method-based JIT, and that's what we're going to hack on today. The other cool thing is that TenderJIT 2.0, so TenderJIT 1.0 only supported x86. TenderJIT 2.0 supports x86 and ARM64. So I think that this means that TenderJIT is actually the very first cross-platform pure Ruby JIT compiler. So there've been other pure Ruby JIT compilers, but I think TenderJIT is the very first cross-platform JIT compiler written in Ruby. It's based off of, so all the techniques that I'm using in TenderJIT are based off of this book, Engineering a Compiler, which I highly recommend. I put a link to this book in the description of the live stream, but it's also here. I definitely recommend this book. It's really great. It's up to date, and it doesn't, like, it talks about like parsing, compiling, everything. So I really recommend you pick up this book. And it uses a bunch of pseudocode everywhere, so there's not like real code to implement. John is asking, in practice, is method-based or LBBV more performant? That is a great question, and the answer is I don't know, and I think the real answer is it depends. But actually, that's one of the reasons I'm trying to write a method-based JIT compiler, is because I'd like to try and compare, like, what does it look like? Like, what would it be like if we were using a method-based JIT versus LBBV? Anyway, I definitely recommend this book. A cool thing about this book is that somebody has put online, like, this book was used as a textbook in a compilers course, and the professor put the compilers course on to YouTube. So, like, this has been super helpful for me. It's like I can go watch videos of the professor giving lectures and their students, and they're asking questions and all that stuff. So, like, get the book, watch the lectures. It's really great. Really recommend it. Okay, so the biggest difference between this method-based JIT, and the LBBV-based JIT is that basically instead of waiting until each block executes, we're just going to compile the whole thing. So we'll go ahead and just like take this entire like control flow graph, just look at the whole thing and compile the whole thing. So even if we never use the false path in this case, in a method-based JIT, we're going to compile the false path. It's going to happen. So that's how it works. Now, unfortunately, this kind of means that like compilation is slower because we have to take into account the whole thing. Like, we're compiling the whole thing, we're doing more, so compilation can end up being slower. And unfortunately, it also means maybe more runtime checks. Like, it's possible that we could have more runtime checks, but it's also possible that maybe we don't. So it's hard to say. One thing is, I think a method-based JIT could possibly generate better machine code because it's able to look at the method as a whole and rearrange that method into something that's a bit more convenient. I also think that we can end up with better register use, and I'll show why that is. Will I show why that is? I will show why that is in a minute here. So let's talk about the architecture of TenderJIT 2 and then look at the register usage, like why register usage might be a little bit better with a method-based JIT, and then we'll get into hacking. So the architecture of TenderJIT 2.0 is we basically take the YARV bytecodes of the method, then we turn those YARV bytecodes into basic blocks. Basically, we construct a control flow graph of the Ruby code itself. So we do a pass to make a control flow graph. Then we take that control flow graph, convert it into TenderJIT IR, which I guess it's like TJIR. I don't know. So we convert it into IR, which means intermediate representation. So we have an intermediate representation. Then we do register allocation on the intermediate representation. Then we convert it into machine code. So there's a lot more passes going on here. Now, the question is, like, why would we want to convert something into, like, why would we want to take this Ruby code and convert it into a control flow graph? The reason I wanted to do that is because I want to start storing local variables in registers. So I want to store, like in this code, for example, the Y variable, I want to store that Y variable in a register. Now, if we have an if statement like this, when we do register allocation, like we need to be able to figure out, like, okay, what register did we store Y in? So like which path we take matters in this case. So like it's pretty clear to us as humans, like, oh yeah, we just like store the Y value in register 1 or something, and then we know, like, oh, okay, yeah, we'll just reuse register 1. But it's not very easy for a compiler to know that, and converting the code into a control flow graph helps the compiler figure out, okay, we need to make sure that this Y variable lands in the same register when we exit these basic blocks. So next question is, like, why should we make an IR? Well, the reason we want to make an IR is because this intermediate representation abstracts us away from the machine that we're targeting, and that means that we can write something that's cross-platform. So we'll take that intermediate representation, then we just go through a translation process that's very simple, just like rote translation of, like, okay, we'll take this instruction and on x86 we'll convert it to this machine code, whereas maybe on ARM64 we'll convert it into some other machine code. So what we're going to do today is we're going to try running optcaret. It's not going to work. It's going to blow up, and then it's going to blow up because we're missing some instructions. I haven't implemented all of the YARV instructions in Ruby or in TenderJIT. So we're going to just implement some instructions and then keep going through that. And I don't think we're going to get optcaret working today. Like, I don't think we're not going to get them all done today. But I think it's a good way for us to, like, look at how TenderJIT is converting things into machine code, and maybe we can see, I might be able to produce some graphs so we can look at the register allocation as it occurs, or also the control flow graphs that we're producing. Kokubun says, as to LBBV versus method-based, I thought you could compile multiple basic blocks together in a tier after LBBV, but then it's technically a separate non-LBBV compiler anyway. And this is a really great point that Kokubun brings up. Like, it's not really an either-or situation. Like, we can absolutely have multiple passes with different JIT compilers in Ruby or in any language. So you could think of, like, LBBV is way faster. Like, we can get machine code cranking out and running way faster, but maybe we do a second pass using a method-based JIT that's slower but produces better machine code. So there's no, like, I mean, I don't think we pick one or the other necessarily. Atmosphere is asking, what is optcaret? Optcaret is a benchmark that it's an NES emulator written for Ruby, and it's just a benchmark that we use for testing. Like, we're using that for testing YJIT, and other compiler like JRuby uses it for testing, and Truffle as well. So we're just going to try running it and see it not work, and then we're going to work on our compiler and hopefully make it work a little bit better. So let's do that now. All right. Let's hide this. So I got TenderJIT here. We're going to do it. So let me make sure I got the right Ruby version. Okay, looks great. So let's try running opt-caret. Yeah, so I made this. This is how you run opt-caret with TenderJIT right now. It's a very, very long command. But TenderJIT 2.0 is using rJIT's bring your own compiler framework. So in Ruby 3.3 or 3.2, I can't remember when stuff is released because I always use Edge Ruby, but rJIT lets us plug in our own. Oh, thank you, Kokoboon. In Ruby 3.3, you'll be able to write your own compiler and plug that into Ruby, so you can experiment with any type of JIT compiler that you want to. And TenderJIT is just using that framework. So we have right here, you'll see this like, where is my arrow? There we go. Yeah, rJIT pause right here, and then also like rJIT call threshold, and that's because I'm using rJIT, or I'm piggybacking off of rJIT's bring your own compiler framework. All right, so let's run this, and it breaks. Okay, undefined method. So as I said, we go through a few passes. TenderJIT goes through a few passes, and it takes it turns the YARV bytecodes into a control flow graph, and we have not implemented this particular instruction here, opt LT LT. So we're gonna do that and then keep going. Opt LT LT is used in the case of, let's just do like vim test.rb. Oh, I guess I have some code in here already, but I'm not using it, so we'll just delete it. Let's make that bigger. All right, so opt LT is used when you have code that's like, you know, array, arrow, arrow, OMG, something like that. So it represents this like less than thing. It's an optimized instruction. So we say, like, if we were gonna do this, we could say like, let's do like ruby -- dump insns. So this will show us the instructions. So we can say like, I don't know, array arrow 1, like that. And you can see right here, here's our opt LT instruction. So we don't have support for that in TenderJIT right now, so we're gonna add it. And I think I have a test for it. Instructions, opt LT test. Oh, come on, Vim, who cares? Let's see. Yes, here is the test. Here is the test for LT. Yes, shovel, thank you. Okay, let's just do something which I like to do, which is copy and paste. We're just gonna copy from, I don't know, what do I have? What is an instruction I've implemented already? Let's just do like opt plus, maybe opt plus test. Sure, seems good. We'll just say like add, I don't know, shovel. So we'll create a shovel. We'll just do like that, right? Double shuffle. I like that name. All right. So we'll do that, and then let's we're gonna compile it, I guess. So I've changed this around a little bit. A lot of the old, like the old TenderJIT 1.0, I would call this method like compile, and I'd give it a method. But what's interesting is the current compiler actually gets, like when the JIT compiler enters, it gets a little bit of context about the callee or the caller. So it actually knows the receiver, it gets past the receiver, and we can specialize based on the receiver. So I wanted to, since I'm manually compiling stuff in the TenderJIT tests, I want to simulate the real world, like what happens in the real world and pass the receiver in as well. So I say like, I want you to compile this method, shovel, and the receiver is going to be self. So, because that's we're just calling this on the test case here. So we'll enable it, call shovel. Boy, I'm a bad Ruby programmer. I don't actually know what this will return. Let's see. Let's do Ruby P. Is that gonna give us back the array? Yeah, nice. John, you're wrong. It's the array. Okay, so we'll say assert equal 1. Okay, and we have 1 compiled method, 0 executed methods, and then we'll say 1 compiled method and 1 executed method and no exits. So let's try running this test. Test instructions. Let's see. Oh yeah, so another thing I gotta do is like I don't want our JIT to I don't want the JIT to run in the test. So I do this thing where I'm like, Kokoboom might know a better way to do this, but right now I'm like, hey, I'm gonna set the call threshold to something really, really, really big so that the JIT compiler never enters. All right, let's do this. Opt LT test. Why don't you just skip resume? I don't know. I'm gonna ping you afterwards, Kokoboon. All right, let's see. What happened? Why didn't it run our test? Test opt LT. Yeah. Okay. Oh, right. I specified a test there. We just want to run the one. Okay, cool. Undefined method opt LT. Let's go do that. We'll implement it. TenderJIT compiler might be in here. Let's do tag yarv. TenderJIT yarv. Okay. So here are all the instructions I've implemented so far. So we got like put string and blah blah blah. But we're doing def opt LT. It's gonna get the program counter as well as access to the instruction. We need to get the the operands for opt LT. And let's see. Let's take a look at what the operands are. So the operands are, it wants a call data, which is an inline cache. So this is the file insns.def, and it's from Ruby itself. And insns.def contains all of the bytecode, like all the instructions, along with their parameters and what they push and pop from the stack. So this is the instruction name. This is a parameter for the instruction. It pops 2 values off the stack, receive an obj, and it pushes 1 value back onto the stack. So we just need the, what do we need? I'm just gonna copy somebody else. Opt EQ, yeah, it's fine. Right there. So we just need the call data, RB call data here. And I did this, I'm like, I'm gonna add an instruction. I like this method here, under method. I'm gonna add an instruction with the name of the method, and then it has the program counter, instruction, and operands. So this is the pass that I was talking about where we're constructing a control flow graph from the yarv instructions. So this part's gonna work, but when we execute this test again, it's gonna break because we haven't implemented opt LT in the actual the IR pass, converting to TenderJIT IR. So when we run this, we'll run it, and it's gonna blow up again, and it's complaining because we haven't implemented opt LT for the TenderJIT compiler yet. So we did the yarv CFG, but we haven't done the IR part of it yet. So let's go do that. In here's the compiler. And for opt LT, like we Yes, Kokubun says he likes using instruction names as method names for compiling too. However, it breaks things like send and dupe. Yes. um, so because there is an instruction named send and there is also an instruction named dupe. So like, of course, there are Ruby methods named send and Ruby methods named dupe. So it's kind of a problem. But anyway, let's see. For opt LT, I just want to implement it the same way that we do method calls. So I'm just gonna make it a method call basically. Let's find opt send without block. I think all we have to do is def opt LTLT context. We take a context IR INSN, and context is our compilation. This object right here, context, is our compilation context. So it contains information about like the current compilation, I don't know, unit, I guess. So yes, absolutely. This is my live stream. We're absolutely using Seattle style method definitions, which is no parentheses. So this context object contains information about the current context. Kyle, why use so many abbreviations? I don't know. I'm lazy. I don't have a good reason for you. I mean, it's like typing stuff out is free, isn't it? But yeah, I don't know. IR is the intermediate representation. It's it's just a list of all the instructions that we're using for the intermediate representation. INSN is the current instruction that we're compiling, information about the current instruction. So that would be this opt LTLT. This object here contains those parameters for the instruction, like the inline cache specifically. So here we're just going to do opt send without block. We're just going to reuse this. What is hacks? That's a very good question. I'll explain it here in a second. So opt send without block, CTX, IR, INSN. Okay, I think this will work. Let's give it a whirl. Hey, nice. We passed the test. Great. So question is, what is hacks? So like I didn't do it right. We need to push something onto the stack. So opt LTLT is going to push a thing onto the stack. We need to tell this context object contains information about objects that are on the stack. And when we were looking at insns.def, let's pull that back up again. Bu insns.def. There we go. We push a value back onto the stack. So we have to simulate that. We have to simulate that when we're writing this compiler. We also have to push a value onto the stack. So we're going to do that. And this is a virtual stack. We're not actually doing this in our machine code. We're just we're pretending that we're doing it so that subsequent compilation steps will know the types that are on the stack. So here we're going to push a value onto the stack, and of course we saw that it just pushes an array onto the stack. So we're going to do that. Basic type. So this hacks, that brings me to this hacks module. I want to get there's certain functions that I need access to in Ruby, because again TenderJIT is being written in pure Ruby, and hacks is like my dirty little secret that it's not actually 100% pure Ruby. We have to it's pure Ruby except for the parts that aren't pure Ruby. Hacks is a C extension that gives us access to some of the low-level stuff in Ruby APIs that we don't normally have access to in Ruby. So in this case, basic type gives us back the type of the object. So I'll give you let's do this in a terminal. I'll give you an example. Ruby, let's do this. Blah 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 -e. Let's see, p hacks dot basic type on, let's say, an array. If we do, maybe I put it under a different name. Did I put it under a different name? Is it TenderJIT hacks? Maybe we need to require it. -r It's R hacks. Yeah, there we go. So we see like here we got the T array. It tells us like, oh, okay, that is a T array type. And we can see like object.new is like a T object. If we pass in, say, 1, then we'll get back T fixed num. Yeah, it's basically, Cocoboon's asking, is this basically C.built-in type? Yes, it is. I wanted a symbol back, so I'm using that. Though maybe I should just convert it to the RJITs built-in thing, because I really, like, hacks is something that I would like to get rid of and maybe push everything back up into RJIT, hopefully. But for now, I have a C extension. Yeah, I've got the gem called hacks as well, and like I think it would be more fun to use it for something else than this. So my goal is to one day convert it to something else. All right, so back to opt LTLT. We pushed this back onto the stack. We're pushing an array onto the stack, so we'll say, hey, the basic type is a type of an array. Out. Oh, you know what? No, we don't want to do this. This is bad. I'm sorry. We don't want to do this because opt send without block already manages our stack for us. We're just reusing it. This one, unfortunately though, opt send without block, it pushes an unknown back onto the stack where we actually know what the type is. So opt send without block is saying like, hey, I called a method. I don't know what the return value of the method is, so I'm just going to push something called unknown. Whereas in this case, we actually do know what the type is, so just leave it how it is for now. I don't really care that much. John is asking, so far we're dealing with handling a specific YARV instruction and updating the intermediate code, but haven't done any actual byte code yet, correct? No, we've generated machine code. We've absolutely generated machine code. So this test is testing that we read through all of the byte code for a particular method, and we generate machine code for that method, then we jump into the machine code. So if we go look at that test, let's take a look at it. So this test here, TenderJIT gathers statistics about the machine code. So when executed methods increases, that value is actually increased via the machine code. So here we're able to say like, okay, we entered the machine code and it increased this value by 1. So we're saying like, yeah, we definitely executed the machine code because the value is increased by 1. Let's see, like, since we're not going to finish, we're definitely not going to finish getting opt-caret working today. So let's take a look at like, we can take a look at the machine code that's actually generated for this thing. I put in some debugging stuff in here, so let's see if I can remember how to do that in this giant font. Okay. So like, what is this? VM block. Oh boy, this is definitely hacks. All right. So here you can see like this is kind of our IR commands. So right here we're saying like, hey, I want you to do a store. I need you to add. This is our statistics right here. We're saying, hey, I need you to look up, like, load the location of the stats struct, find the offset of the executed methods in the stats struct, add 1, like increment it by 1, and then store that incremented value again right here, this store. So that maps directly to the statistics that we are gathering in that test case. So then right here, we're saying, hey, give me all the basic blocks for the YARV instructions. We translate the control flow graph for those, the YARV control flow graph. Then here we say, hey, I need you to assemble this into machine code. We ask the IR to assemble the machine code. And then we write that out to the buffer right here. And then we mark the buffer as executable right here. And then right here we get the address of it, and that is what we'll jump into. Atmosphere is asking, what is the software I use to draw the arrows? I can't remember the name of it. It's called Screen Brush. Screen Brush. It's a good tool. I like it. All right, so let's just pull that out here. Let's just disassemble it. So if we disassemble it, we can see, let's run the test again. So right here is the machine code that we generated. It doesn't have any comments in it right now, but you can see like this is it. We can also do, let's see if we can show something more fun. Translate CFG. Let's go to IR assemble. Yeah, here. So inside of the assembly method, we do register allocation. So like we assign registers to it, and the register assignment depends on the platform that we're dealing with, because x86 has different registers than ARM, of course. Here I added a thing so we can take a look at the register allocation. So let's just do if true here, so we can kind of look at it. If we do that, oh, it blows up. Oh, because I wrote wrong Ruby code is why. Say if true or debug. Okay, I'm gonna bring the font down here a little bit because the ASCII art doesn't look good when it's this big. There we go. Hopefully this is still at least somewhat readable. This diagram here, yes, here we go. So this diagram is showing our intermediate code along with the registers that we allocated. So the way that we deal with these, the way that we convert this into machine code is in our IR, we pretend that we have an infinite number of registers. But the trick is we can only ever write into the register once. So we have an infinite number of them, but we can only write into that register once. And these values here across the top here, this like 0, 1, 2, all these values here across the top, those are our infinite registers. So we happen to use, in this case, we happen to use 22 registers. And the job of the register allocator is to say, okay, we got to rein this in here. You used 22 registers, but we got to pull that down to like 32 or however many registers we have, like the number of registers we have available in our register allocator. Now, we can see here, these are the intermediate codes here. So like, for example, we have a load P, it loads a parameter. It has one output register, but it has no input registers. This is just us. We want to load the very first parameter. More interesting here. Let's try to find a more interesting instruction, like maybe infinite registers. No, this isn't Grandpa's 8008. No. Okay, so we have right here, like let's say, I don't know, this sub instruction. This is like subtracting a number. We have two input registers here. This, is that right? Hold on, I gotta look at this. Yeah, two input registers here. Where was the sub? Yeah, here we go. So two input registers, in 2, in 1. Our input is an immediate, which is the number 8. Then we have a temporary, like one of those infinite registers. However, this is the infinite register number 5 is the one that we're using. And then our output is going to be infinite register number 10, or temporary number 10. Now along here, these are the actual registers that the register allocator assigned to. So it said like, okay, for register number 1, I assign to you register X12, the physical register X12. And what's kind of cool is on this graph, we can see the life of that register. So this X12, like this X12 register, it actually lives for a very long time. So it lives all the way down to the bottom here, right here, and then it's done right there. And what that means is we can't use, during this entire time, all of these instructions, we can't write into register X12 because it could be used later on. You can see like right here, X1 is pretty short-lived. X9 is also pretty short-lived. Well, it's a bit longer. Then like here, X10 is short and it died, like it's done being used right here. So the register allocator decided that, hey, okay, infinite register 5, it's gonna get 10. So it's like, oh, you got done with it here, so we're just gonna start using it here. And it's like, oh, right here, this one's like, well, 12 is in use, 9 is in use, 10 is in use, but we need another register here, so we're gonna use 11. That's basically how the register what the register allocator does to decide. And the allocator that I'm using is I wrote a graph coloring algorithm, which this is covered in that compiler book. But I think, let's look here. I did a thing. Let's see if I still have it in code here, where it'll output a dot file. Let's check. Yeah, let's come into here to the register allocator. Let's see. 2 dots. Yeah. So those graphs that I was showing you, the interference or the control flow graph. We also have a graph representing all of the registers that are included. I had them output dot files so that we can view them in GraphViz and kind of like figure out what's going on. I use these GraphViz files a lot to debug the stuff. So let's actually just generate it for this particular method, and maybe we can take a look. So we'll run this again. Should have ended up with a couple new dot files called ifgraph and cfg. Let's see. Oh, actually I have a bunch of them sitting around already. Let's delete them. cfg dot star if dot star. Let's do it again. And then dot. We'll create a PDF. Let's look at the interference graph first. Oh, okay. Hey. Hopefully that looks good. Yeah, okay. Okay. So these are like, if we take this graph, I guess some of the colors are kind of messed up, but like, let's look here. I want to look at that graph, and at the same time we look at that graph, let's also look at that ASCII output, because I think this will help illustrate what's going on. So here in our ASCII output, you can see like, oh yeah, we've got X12 here, and at the same time, X12 is alive right here, and at the same time we have X9 here and X10 here. And that's because those three registers are what they call interfering. They interfere with each other, meaning that they have to be alive at the same time. And that's what this graph is illustrating right here. Which registers have to be alive at what time. So these numbers here, these are our infinite register numbers. And you can see like the different colors it assigned to them. Those different colors represent the physical register that we're going to use. So right here, let me try and bump up the font on this thing. See if it'll get bigger. Yeah, there we go. Hey! No, go away, arrows. I don't want you here. Stop. Okay. It's not going away. Stop. There we go. All right. So you see right here, infinite register 6, 7, and 8. They're all able to use the same physical register, purple. And then we assign that color purple to an actual ARM register. So if we go take a look in our ASCII output here, we should see like, okay, here's infinite register 6, here's infinite register 7, infinite register 8, and you can see indeed we assigned all of them the X11 ARM register. All right, I think it's been an hour, so I'm gonna stop here. I'm gonna stop here today. I'll try to do more hacking on this later. Let's go back to the keynote for a second. Keynote. So next time, Cocobone, it's amazing how far you've gone while still not compiling opt-LT-LT. So I do prepare for these live streams, and I actually kind of say, like, I saved opt-LT-LT for the live stream so that we could do it together. But yes, next time I want to do some LSP stuff. I cajoled a special guest into joining us next time, so I'll schedule that in the on the YouTube thing. We're gonna do it next month. I'm trying to do this like once a month so that I can get kind of a better cadence. I think once a month will probably be a good, I don't know, time. So next time we'll do some LSP stuff. I want to say thank you all for coming. It was really. Oh, John, what happens if you run up carrot now? Yeah, let's. Man, why did I not do that? Let's do that. Where is it? Desktop me. Let's do it. If we run opt carrot, we'll get. What are we gonna get? Opt carrot. Run it. And we're missing set in. So set in is our next instruction. So we made it past opt LT, but we got to do set in for our next instruction. All right, back to Keynote. Thank you all for coming. It was really, I like doing this. It was good to have all of you here for a Friday. As I said, we'll do LSP stuff next week, and I don't think I have any more slides. So thank you all. Have a good weekend.